So in last class we started discussing about fields, and I discussed about these topics in fields, which was Galois field, which we represented as GFPN. Okay, where P is this is a prime number. Okay, so we discussed a case wherein this value of n is 1. So we represent it as GFP. Okay, and because this P is a prime number, so we extensively use this Galois field, this one, wherein the value of P is 2. Okay, so we make use of these two Galois fields extensively. One is this GFP and another is this GF 2 raised to n. So here this value of n is greater than 1. Fine. So why do we use these fields in cryptography? Because in most of the cases we make use of fields. The reason is, in the last class I told you that in the summary table, I have shown you that while using fields we can perform all the operations, that is addition, subtraction, multiplication and division. Right, so all the operations can be performed, and since in cryptography we need to perform all these operations often, so we make use of fields in cryptography. Okay, so that is the same thing. Okay, so we need to use fields in cryptography because they are preferred actually, and the use of fields is preferred in cryptography, so that we can work in GF2 raised to n. Okay, this set which I was talking about, which uses a set of 2 raised to n elements. Okay, and the elements in this set are n-bit words. Now what are these n-bit words? I'll tell you later that how do we create these words out of these sets, these elements, okay, in this particular field. Okay, so since we deal with these n-bit words, so we make use of polynomials, okay, which are n-bit words. Fine. And how do we represent these polynomials? How do we perform operations using these polynomials? We'll discuss in later slides. Because when we use polynomials, then perform these operations, these addition, subtraction, multiplication, and division, and modulus as well, it becomes easy. Okay, so that is why we make use of polynomials with fields. Okay, so we will be using both of these things for the coming topics. Fine. So now we have two choices if we want to use fields. One is this set, okay, and another is this set. Now we can make use of any of the set which I was telling you previously. We extensively use these two sets, but in this set, this first set, GFP, the problem is that this P is the largest prime number, which is less than 2 raised to n. Okay, so we cannot make use of all the elements available. Say for example, here this value of n is 4. Okay, and the largest prime number less than 2 raised to n, so 2 raised to n become 2 raised to n means 2 raised to 4 becomes 16. Okay, and the largest prime which is less than 2 raised to n is 13. But in the set, if this set is of 16 elements, which is 2 raised to 4, so we'll be having numbers from 0 to 15. So out of these 16 elements, we will not be able to use these 3 elements. Okay, so that is the problem with this kind of fields. But in this field, there is no such problem. We make use of each and every element present in the field. So it uses a set of 2 raised to n elements, and the elements in the set are n-bit words. Now again, I'll tell you how do we create these words. Now see, this is the example of creating n-bit words. Say for example, I have this Galois field, which is 2 raised to 2. Okay, so 2 raised to 2 means it will have 4 elements. Okay, so 4 elements here mean element, that means n-bit words. Okay, we can call them element or n-bit words. N here is 2. Fine. So 2-bit words होंगे यहाँ पे, और कितने होंगे? They will be 4 2-bit words. Okay, and these 4 2-bit words are these one. Okay, they will be 0 0 0 1 1 0 and 1 1. Okay, so this is how we create element or the n-bit words for any given field. Now this is how we can define this example, or the addition and multiplication operation using this particular field, which is gf 2 raised to 2, which is of the form gf 2 raised to n, which was the second case. Okay, this case. So using this field, I'll be telling you that how do we perform addition and multiplication. So this is an example. Okay, so we are having this field which is having 2 raised to 2 elements, that means 4 elements, and each element is a 2-bit word. Okay, so here these are the words we are having. Okay, and we are performing this addition operation, which we represent like this. So when we perform addition operation over these two words, then the result will be 0 0. Okay, when we perform addition of 0 0 and 0 1, the result will be 0 1. For 0 0 and 1 0, the result will be 1 0. For 0 0 and 1 1, the result will be 1 1. So that is how we add these values. But here you have to see that this identity element for this particular field is 0, because we are performing this addition operation. So for addition operations, the identity element is 0, and for multiplication, this identity is 1. Okay, so here you can see that for this entry, which is 1 1 and 1 1, our result is 0 0. So this thing you have to keep in your mind, that when you are adding similar values, then the result will be 0. Okay, so this is you can say this is XOR operation, which I also told you in the previous class. Okay, while using field, जब हमने दो values का एक field बनाया था, and I told you that addition operation is equivalent to XOR operation, and this multiplication operation is equivalent to AND operation. Fine. Now here in this table, this multiplication table, one thing we have to see, that wherever we get this value 1, okay, in this table we are getting it 3 times. So wherever we get this value 1, that means these words are multiplicative inverses of each other. Okay, because when we multiply the given number and its multiplicative inverse, then we get a value which is equal to 1, or if it is not equal to 1, then its mode for the given value of n, it must be 1. Okay, so wherever we are getting this value 1, which means that these numbers are multiplicative inverses of each other. So here in this case, this 0 1 and 0 1, they are multiplicative inverse of each other, because we'll be calculating multiplicative inverse of the polynomials as well. So we need to understand it. Okay, so in this case, this 1 0 and 1 1, they are multiplicative inverse of each other. Okay, here this 1 1 and 1 0, so they are same numbers. ये वाला जो set है 1 0 and 1 1, and this set 1 0 and 1 1, they are the same set. It is 1 0 1 1 1 0 1 1. So they are obviously, if 1 0 is multiplicative inverse of 1 1, then 1 1 will be multiplicative inverse of 1 0, right? So these three multiplicative inverses we have for this given field, right? So this is how we represent the addition and multiplication operation using this Galois field, which is Galois field of the form 2 raised to n. Okay, now we'll start discussing polynomials, because dealing with polynomials makes it easier to perform operations, any operation which is addition, multiplication, subtraction, or division. So we represent a polynomial of degree n minus 1 as this expression, okay, wherein this xi, these xi, so each and every term is comprised of this a part and x part. So this x part is called the term or the polynomial, and this a part is called the coefficient of the given term, right? So and one more thing, this here you can see this term, each and every term is having some power, okay? It starts from 0 to n minus 1, okay? Because because this is degree n minus 1, when we say it is polynomial of degree n minus 1, it means that it will be having terms or polynomials of of power which starts from 0 to n minus 1. Okay, so here we can see that these terms are having power from 0. This is x0, this is x1, next will be x2, and the last will be x raised to n minus 1. Just like these terms, these coefficients also will represent them from 0 to n minus 1. So this coefficient A0 is the coefficient for ith term, or this A0 is coefficient for 0th term. Okay, so this subscript and this power of the element, they will be same, right? Now this power of x defines the position of the bit in n-bit word. So this thing I will tell you with the example, that what does this point mean. Okay, these 2 points, the coefficient of terms define the value of the bit. Okay, so I'll show you one example, so these 2 points will be clear to you. Now it says that how we can present this 8-bit word. This is the 8-bit word, and how we can represent it using polynomials. So we have to use these bits for creating the polynomial. Okay, so this will be the value of coefficient, right? So here you can see we are having these coefficients, okay? These are the terms, this x raised to some power, these are terms, and these are coefficients. So we'll go back to that point. So it says that power of x defines the position of the bit in n-bit word. So here you can say that this bit is at 0th position. Okay, so this power will tell you the position of this particular bit. Okay, this bit which we are writing over here. And the coefficient of term define the value of the bit, which will always be 0 or 1. So we'll be using only these two values, 0 and 1. So the coefficient will be 0 or 1 depending on this word given. So यहाँ पे जहाँ पे भी 1 वैल्यू है कोफिशिएंट की या इसकी बिट की, उसी के कॉरस्पॉन्डिंग पॉलिनोमियल में कोफिशिएंट की वैल्यू 1 होगी. तो हियर यू कैन सी दैट एट 0th position, then at the first, second, third position, then at 4th position, and then at 7th position we are having a coefficient, and other coefficients are 0. So here we can cross check, this is 0th position, this is 3rd, 4th, and 7th, right? So these coefficients will these define the value of the bit which is given to you, okay, in form of this word. And the power will be the position of the bit in n bit word. So if we are talking about, say, this particular part of this polynomial, that means it tells you that at this position the value of coefficient is 0 and the position you are talking about is 5, okay, because its power is 5. Now we can simplify this given polynomial by eliminating these values which are having 0 as coefficient, because they are of no use, because you need to multiply this 0 to this term or this polynomial, so ultimately you will get a 0 out of it, right? So it will be the first simplification wherein we have just written the values which are not 0. Okay, so this one and this one, this one and this first one. Okay, so these entries we are having. Now the second simplification, it simply emits this entry 1, because when we multiply this 1 with any number you get the same value. Okay, so this will be the result. Okay, so this is polynomial representation of this 8-bit word. Okay, so it says that the term is totally omitted if coefficient is 0, as I told you, and coefficient is omitted if it is 1, right? So यहाँ पे जो coefficients 1 थे उन coefficients को हमने omit कर दिया, and also x raised to 0 is 1, fine. So यहाँ पे भी x raised to 0 की जो value है that is 1, fine. So ये वाली value 1 हो जाएगी, 1 into 1 will be 1. So this is how we convert any given word into polynomial. So we'll be using these polynomials for calculations. So there is this is the reverse way. So we need to find the 8-bit word related to the given polynomial. So this time the polynomial is given and we need to find the word. In this example, what did we do? We were given the word and we used to we were finding the polynomial, right? So here what we will do will be this n is given over here, okay? So we'll be writing the expanded form of polynomial for it. Now how will we do it? इसके अंदर जो जो powers नहीं available हैं, for those powers will be writing coefficient as 0 along with their polynomial, right? तो इसके अंदर this 1 is present, 2 is present and 5 is present. So इसके अलावा what polynomials are left? 0th position is left, then 3rd position, then after this 4th position, then 6th and then 7th. Now since this n is equivalent to 8, तो polynomial हमारा किसका कितना बनेगा? n minus 1 तक, means 7 तक will be going for creating the polynomial. Fine. So here you can see this coefficient is 0 for 0th element, for 3rd element it is 0, for 4th element it is 0, for 6th and for 7th. Okay, so now we have this polynomial form. Now we can create the word out of it. Now in word, what we will be doing? We'll be using this power for checking out the position of the bit, and we'll be using this coefficient for checking out the value of the coefficient. Okay, so at 0th position the value of the given bit will be 0. At first position the bit will be 1. So here you can see this is 0, this is 1. At second position as well it will be 1. Here it is. At third and fourth they are 0 0. At fifth it is 1. And then at sixth and seventh it is 0 0. Okay, so this is how we can create a word out of the given polynomial. Okay, so this is the two-way process. अगर word given है you can find out the polynomial, और polynomial given है you can find out the word. Okay, now we'll be talking about the operations which will be performing on polynomials. Okay, so we'll be covering the addition operation, multiplication, subtraction, and division operation. Okay, one more operation which is modulus, which we'll be using in case of multiplication and division as well. Right, so we'll be discussing all these operations one by one. So these two fields we use in polynomials, right? So that is the same thing we discussed in initial slides. So any operation on polynomials involve two operations, okay? Operation on coefficient and operation on polynomials. So we need two fields, one each for coefficient and polynomials. So because we need to perform two operations, one on the coefficient and one on polynomials, so we'll be requiring two fields. So we'll be making use of these two fields, okay? Galois field 2 and 2 raised to n. Now since coefficients are made up of zeros and ones only, so we can use this field, okay, here, because the size of this field is 2, okay, the number of elements we are having is 2 only, so we can use this field for the coefficients, and for polynomials we can use this field, क्योंकि जो polynomial part होगा या जो terms होंगी given polynomial की, they will be in powers, okay, जैसे हमने previous example में भी देखा. So यहाँ पे we are having powers of x, right? और जो coefficients की values हैं वो हैं zeros and ones only. Okay, so coefficients के लिए we can use this field, this gf2 field, and for polynomials we'll be using gf2 raised to n fields. Now the operations. So add or subtract, when we perform this addition or subtraction operation on polynomials, so we add or subtract depending on the operation which we are doing. We perform the operation on corresponding coefficient. जैसे for example अगर कोई x क्यूब का एक polynomial है, उसको जब हम ऐड करेंगे तो x क्यूब वाले के साथ ही ऐड करेंगे, राइट? और इसको कभी भी हम इससे छोटी या बड़े पावर वाले पॉलिनोमियल के साथ ऐड या सब्ट्रैक्ट नहीं करेंगे. Then we have multiplication operation wherein we multiply all the terms by each other. तो यहाँ पे we do not see कि पावर छोटी है या बड़ी है, we multiply each and every term with each other. So this is an example given. So say these two polynomials we have fx and gx. So fx gx का जब हम addition करेंगे, so in that case we'll be adding or subtracting the corresponding coefficients. So x3 का जो addition है that will be with the x3 only. Okay, so you can see here there is no coefficient or no term of x3, so it will be written as it is. Here we are having these two terms of x square, so x square and x square, they will be added and you get 2x square. So just like this we can add or subtract the given polynomials. Okay, this is subtraction. Now when we multiply it, what we get, you multiply each and every term with the other the polynomial or the term of the other polynomial. Okay, so here this x3 will get multiplied to each and every term of gx. Okay, and when you add, then these powers when you multiply these terms, then these powers get added. So when you multiply this x cube with x square, the result will be x raised to 5. So this is how we perform multiplication. You all must be knowing these operations. These are simple, very simple operations. Now comes the division. So we can write any polynomial in the form fx qx, that is the same expression we have used in integer division. Okay, so this remainder, it can be written as is fx mod gx. Okay, so this is the divisor and this is the dividend. Okay, this is quotient. Now if gx has no divisors other than itself and 1, then we call it as a irreducible polynomial. Okay, so we'll be using this irreducible polynomial for calculating the mode. Now why do we calculate mode? Because while doing multiplication, the power of the given polynomials exceed from n minus 1. So that is why we need to calculate the mode. जैसे हम लोगों ने previous examples में जितने भी सिफरिंग टेक्निक्स की हैं उसमें we have range from 0 to 25. Fine. So as soon as we exceed this value 25, what did we do? We found out mode. We calculated mode 26. Okay, so in this case as well, when we multiply two polynomials, so there are very good chances that the power of the given polynomial exceeds n minus 1, which is not permissible, right? So in that case we have to find out the mode, and that mode is found out using these irreducible polynomials. So the polynomials which do not have any divisor other than itself or 1, we can also call these kind of polynomials as prime polynomials. Okay, and we can also call them irreducible polynomials. Okay, so we'll be using these irreducible polynomials for finding out the mode. So this is how we perform division. I'll show you an example also for division of polynomials. Fine. Okay, so after this we have covered this addition, subtraction, multiplication, and then division. Okay, now we'll discuss this modulus operator and we'll discuss in detail about those irreducible polynomials. So that is the thing, I was telling you that sometimes this multiplication results in a polynomial of degree greater than n minus 1. So then in that case the polynomial is reduced modulo some irreducible polynomial mx of degree n, ताकि हम जो ये डिग्री इसकी इंक्रीज हो गई है फ्रॉम n minus 1, we can take it or we can bring it into the range, right? So what we do in when we find out modulus, so we divide by mx, which is the irreducible polynomial, and then we keep the remainder only. Okay, so this remainder will be giving you a polynomial which will be having a degree not greater than n minus 1. So this modulus operation, it forms a finite field, and just as the Euclidean algorithm can be adapted to find the GCD of two polynomials, the extended Euclidean algorithm can be adapted to find the multiplicative inverse of a polynomial, right? So we can use the same algorithm for finding out जैसे हमने integers पे operate किया था वैसे ही we can operate on polynomials as well. Okay, using Euclidean algorithm we can find out the GCD of the given polynomials, and using extended Euclidean algorithm we can find out the multiplicative inverse of any given polynomial, right? So for the sets of polynomials in this field, a group of polynomials of degree n is defined as the modulus, and such polynomials are referred to as irreducible polynomials. So I'll show you some examples of irreducible polynomials. So these are polynomials up to degree 5, right? And these polynomials are irreducible. Irreducible means they are prime as well. Okay, and these polynomials can be used to for finding or for calculating the modulus operation, for carrying out the modulus operations. Okay, so here this example we have for addition. then we cover an example for multiplication as well. So addition और subtraction हम same way में कर सकते हैं, right? So here it is asking for adding these two polynomials. This is first, this is second, and this is the field we have. Okay, now this means 2 raised to 8 means the length of the given word is 8-bit. Okay, so we use the symbol this to show that we mean a polynomial addition. Okay, so you have to use this symbol for addition and like this for multiplication, okay, as we used earlier, right? So what we do is we'll first create the whole polynomial out of it. Now we know that this is an 8-bit word. So इसमें जहाँ पे जितने coefficients नहीं है उनके लिए हम 0 put करेंगे, and for rest which are available over here उनके लिए we'll be putting 1. So इस case में here you can see we are having polynomial for first position, second position, and fifth position. For rest of the positions, the value of coefficient will be 0. So you can check it from here. This is 0th, this is third position, fourth position, sixth, and seventh. So they all are 0. Right. So just like this, we'll be dealing with the second polynomial. Okay. यहाँ पे 0th के लिए 1 value है. So we'll be writing 1 over here. And then we'll be adding these two polynomials. Okay. So ये क्या होगा, XOR operation होगा. If you want to go for this shortcut, okay, shortcut में हम लोग क्या करेंगे, we will be writing the bits and you'll be simply performing the XOR operation, okay, bitwise, right? So यहाँ पे क्या हो जाएगा, 0 plus 1 gives you 1, 1 plus 0 again gives you 1, 1 plus 1 gives you 0, right? तो मैंने आपको पहले भी टेबल में बताया था. Okay, 0 and 1 gives you 1, 0, 1, 0, 0. So the result will be, इसको हम discard कर देंगे, this will be discarded, this will be discarded, this one, and yes. So we are left with these 4 entries of polynomials. One is this x raised to 5, then x raised to 3, then x, and then 1. Because this x raised to 0 is 1, right? Okay, so this is the answer we get after adding these two polynomials. Fine. Okay, so that is it is only telling you the same thing, that there is the shortcut of performing the XOR operation over these bits, these bit words, okay, and you can perform this XOR operation bitwise. Now this additive identity and additive inverse we have to talk about. So the additive identity of a polynomial is a zero polynomial. जैसे integers के केस में भी हमने किया, जो मैंने आपको previous table में भी बताया था, जहाँ पे value 0 आएगी, that means they are for addition operation the identity element is 0. Okay, और additive inverse का क्या केस है, that each and every polynomial has the additive inverse and it is additive inverse of itself only, right? So you can check it from that table as well, this one. Okay, so in the entry wherein you are getting this identity element, so you can check, this is 0 0, this is 0 0, okay, this is 0 1 and 0 1. So you can say that they are additive inverse of each other, right? Okay, next comes this multiplication. So as we already discussed that this is done in GF2, okay, the coefficient multiplication we do, okay, for coefficients we use this field, okay, and when we multiply this xi with xj, then the result is xi plus j, and the multiplication may create terms with degree more than n minus 1. Us case mein what we will do, we'll be finding out the modulus, we'll be calculating the modulus. Okay, now this is the example. So this is one polynomial, this is another polynomial, and this is the given set. So here also you can see, you can find out that how many bits are there in the word. Okay, and this irreducible polynomial is also given, because whenever you'll be, you know, multiplying these polynomials, so there are chances कि आप इसकी जो power है वो 8 से बड़ी हो जाए, right? So in this case you can see also this x raised to 5, when you multiply this x raised to 5 with x raised to 7, the result will be x raised to 12. So we'll have to you know, bring it to x raised to 8 only. Fine. So this will be the solution, right? Not x raised to 8, you'll have to bring it to you know, up to x raised to 7, because we take it up to n minus 1 only. So here what we have done is, this is uh, the first polynomial, this is second polynomial, and this is the operation, multiplication operation, polynomial multiplication. So we are simply multiplying this x5 with this whole set, then x square. So these are polynomials of this particular, these are the terms of this particular polynomial, okay, x. So one by one we are multiplying each and every term of this polynomial with this whole polynomial, right? So this is the result we get. Now when you add it, the terms which are having same power will be, you know, this is 1x raised to 9, this is 1x raised to 9. So 1 plus 1 gives you 0. 0x raised to 9 will be there. Okay, so this term will be discarded, right? So herein this you can see that a result will comprise of this x raised to 12, because there is no other entry for x raised to 12. Okay, x raised to 8 we have here and here, so they both will be discarded. Then we have only one x raised to 7, then this x raised to 6 will be discarded, 5 will be discarded, 4 will be discarded, this 3 will also be discarded. Okay, and we are left with x2. So in result we are having this x raised to 12, x raised to 7 and x square. Now this is out of the bound. Okay, so we have to find out its mode with this given irreducible polynomial. Okay, so when we find out its mode, then what will we do? We will be dividing this value, this polynomial with this polynomial, and the mode, the result of mode is always remainder. तो इनको जब हम divide करेंगे तो जो भी हमें remainder मिलेगा, that will be our result. So in this result you can see the maximum you know, power of polynomial we are having is 5, right? So this is into the range now. Now how do we divide it? How do we divide these polynomials? I'll show you the example. You can see, okay, so this is the divisor and this is the dividend. Okay, so you will divide first of all with x raised to 4, because the maximum power we have is x raised to 12. Okay, so these powers will get added, right? So when you multiply this and this, you get this polynomial, right? Then we add these two polynomials, this one and then this one, we get this polynomial as result. Then again we'll see कि maximum power क्या है, इसकी maximum power 8 ही है, so we will be having, you know, next entry in the quotient as 1. Okay, because 8 से ज़्यादा हम power यहाँ पे ले नहीं सकते हैं, right? So we'll be getting this polynomial, and after adding these two polynomials we'll get this result, okay, which is the remainder, okay, in which we are interested. Fine, so this is how we you know, find out the multiplication, this multiplication of these two polynomials, right? And we keep the result which we get out of these which we get out of this multiplication operation, we keep this result in the range using mode operation. Okay, and mode using this irreducible polynomial. Fine. So that is the division part. Now this multiplicative identity, so for multiplication operation the identity is always 1. Okay, for addition it is 0, for multiplication it is 1, and the inverse we have to find out using the extended Euclidean algorithm to the modulus and the polynomial, just like we did with the integers. So I'll show you one example also for this कि हम कैसे इसका use करते हैं. This extended Euclidean algorithm, how it is used to find out the multiplicative inverse of the polynomial. अभी तक हमने integers का inverse निकाला है, multiplicative inverse. Now we'll be calculating the multiplicative inverse of the polynomials as well. Right? Okay. So this is how we do it. This is the given field. Fine. And you have to find out the inverse of this polynomial modulo this polynomial. Okay, now how do we do this? The process is same. Instead of integers, now we are dealing with polynomials, right? So this will be r1, this will be your r1, and the dividend will be the r2, and when you divide these two values you get a value of quotient and a value of r. Then we replace these values, this value come over here, this value comes over here, and then we again divide these values, we get a quotient and a remainder. Okay, so here we are getting 1, so that means this given polynomial has a multiplicative inverse. Now how do we calculate it? Will be extending the algorithm. This t1 is 0, t2 is 1, and t will be, here will be ignoring that minus sign. Okay, so वहाँ पे जैसे हम minus use करते थे, minus sign हम लोग consider करते थे, यहाँ पे minus sign consider नहीं होगा. Right, so this thing will be calculating using t1, t2 and q. The expression will be same. There the expression was t1 minus q into t2. तो यहाँ पे जो minus sign है that will be ignored. Right, so again these values will be replaced, and as soon as we get a 0 over here, so this will be the result. Okay, this will be the multiplicative inverse of this given polynomial. Okay, so this is how we calculate multiplicative inverse using extended Euclidean algorithm. This is one more example for finding out the multiplicative inverse of a given polynomial. So this is the given polynomial. Okay, this is the value of the divisor, right? Sorry, this will be the dividend. This will be the dividend and this will be the divisor. Okay, fine. Now this will be r1, this value will be r1, this will be r2. You'll be dividing them, you'll be getting a value q and then r, and this process goes on, right? So here you are getting 1, that means the multiplicative inverse you can find. Okay, so again this process, and here at this last step we get the multiplicative inverse of x raised to 5. Right, so this is how we perform operations on polynomials. Okay, so we have performed addition, subtraction, multiplication and division operation and modulus as well. So we'll be using these polynomials in the coming classes, for understanding the cryptographic algorithms. Okay.